All right, so we're going to start UA5 unknown angles using reasoning. Okay, and before we get to the notes, let me just relate this to what we were doing in class. So basically, in class, what I had you do, I had you find all the missing angles in a diagram and then explain to the class, give a reason for your answer. So essentially, you started out saying, well, we know that these lines are parallel. And we used previous known facts and information to reach these conclusions that, in this case, let's say we name these angles 1, 2, and 3, 4, and 5, okay? Given that A and B are parallel, we know that angle 3, the measure of angle 3 is equal to 39 degrees because it's an alternate interior angle with 39, based on that alternate interior angle theorem. So you reach this conclusion based on some known fact about alternate interior angles. Okay, and so you're just providing an argument for your answer, reasons for your answer. Well, formally we call that a proof, and we've been doing that in class in the form of like presentations and verbally doing it. Well, now we're going to get down to kind of what a proof looks like when we write it down. Okay, so it's going to be a written proof, a written explanation justifying your reason for your answer, or the conclusion you make. And so we're going to start with a definition, right? Because we're talking about using reasoning. And we're going to just say a reason is just an explanation. And the main idea of this lesson is that we're going to use logical arguments using reasoning, explanations to arrive at a conclusion. Okay, so we've got different kinds of reasoning. We've got inductive and deductive. Now what you're going to be using is often a combination of both. What we were using in class was mostly deductive. But let me explain inductive first. Okay, inductive reasoning is where you reach a conclusion. So you arrive at your answer. And your conclusion is known as a conjecture. Like I say that my answer is this, my conjecture is this, based on some kind of a pattern you observe. Okay, that's inductive reasoning. So inductive reasoning deals with probability, or basically uncertainty. Like I'm 80% sure based on this pattern that my answer is correct. Okay, in general, it goes from some particular event, like one event, and we use that one event to explain everything, and we go from the particular to the universal. A conjecture is just an educated guess. About how the pattern is going to continue without knowing for an absolute fact that your guess is accurate. Okay, so this is how kind of the flow right here. Inductive reasoning. If you're going to use inductive reasoning, that means you're going to look for some pattern based on that pattern. You're going to make some kind of educated guess, reach a conclusion. So you're going to say that's making a conjecture. And then after you make a conjecture, basically you say that this is my answer, I think, then you're going to try to verify that conjecture. Okay, so you're going to reach a conclusion and then try to verify your conclusion. All right, so an example, right? Here's a pattern. We're going to predict the next two numbers in the sequence, right? 1, 4, 7, 10. We don't know for sure, let's say, what this next number is really, but we can look for a pattern and make an educated guess. 1, 4, 7, 10. Well, these numbers are increasing at a constant rate of +3 each time. That's what it looks like it's going on. So most likely the next number should be 13, and the next number after that should be 16. All right. So you do this one. See if you can come up with what the next two numbers are. 1, 1, 2, 3, 5, blank, blank. Okay, this one's a little bit more difficult, and we'll talk about this one in class when you come back. Okay, another example of inductive reasoning, right? All brown dogs in the park are small dogs. So that's our particular event. We're at one park, and all the dogs in this park, or all the brown dogs, are small. Therefore, we're going to apply that to all small dogs are brown. Doesn't mean our conjecture is accurate, but based on this one particular event, we're going to apply it to the universal. Okay, example 3, sketch the next figure in this pattern. Okay, well, we have a triangle, we have a square, and we have a pentagon. And in these, we've got all the vertices being connected with these diagonal lines. So the next one in the pattern should be a hexagon. Try to draw a trapezoid and then another trapezoid below. Right, and in this case, we're going to connect all vertices. So start with one vertice and join it with all others. Then move to the next vertice and do the same thing. All right, so we're not doing this randomly. We have some little system to it. Now go to the next vertice. Notice this one already has one of them, so we just need to draw 2 more. This one already has 2, so we just need to draw 1 more. And these are already done. Okay, so there's our next figure in this pattern using inductive reasoning. All right, let's go on. Okay, a second type of reasoning. And again, we're often going to be using both types. One is patterns, and one where we reach a conclusion that's made by a logical series of facts. Like, we know this is true. And we know this is true. Therefore, our conclusion must be true. Okay, so we're going to use facts. We're going to use definitions. We're going to use accepted properties. Basically, anything in our little toolbox of prior knowledge of things we know to be true. Okay, so deductive reasoning deals with certainty and goes from the universal to the particular, right? So from the big to the small. So deductive reasoning. Kind of the flow is, we're going to take things that we know for a fact are true. Facts, and I know that we just kind of wrote this. Definitions. Accepted properties. And from all these things that we know to be true and are certain of, we know the definition of, we can take all that and arrive at our conclusion. Right? And this is a logical argument. Okay, so we're going to be doing proofs using reasoning and apply it to geometry. Okay, so a geometric proof. It just involves writing reasoned, logical explanations that use definitions. Based on the definition of a square, I know this. Axioms, postulates, and previously proved theorems. Now, I know we haven't really defined axioms, postulates, theorems. Maybe we can write that down formally when you come back to class. But these are just statements of fact or truth about certain things. We have the alternate interior angle theorem. We have the corresponding angles postulate, right? And we can use these to arrive at a conclusion about a geometric statement. And again, that's what you were using here when you did this verbally. These lines are parallel. Okay, so that's some property about this diagram that we know to be true. We already know the alternate interior angle theorem, so therefore we can say angle 3 has a measure of 39 degrees based on the alternate interior angle theorem, right? 2 and 4 have to be congruent. 1 and 63 have to be congruent. And these are based on things that we already know to be true about parallel lines cut by a transversal. Okay. So we're going to prove the vertical angle theorem using deductive reasoning, things that we already know to be true, to make our conclusion. Now, the vertical angle theorem just says that these vertically opposite angles are congruent. Okay, we know that the angles on a line add up to 180, and we're going to prove the vertical angles are equal in measure. So when you do a proof, and you basically write out in words how you would explain that these two angles have to be the same measure, you come up with a plan. Sometimes you do a little scratch work, and then you list out your statements and the reasons you know those statements are true. All right, and you do it in some kind of a systematic order, starting with the most basic property, you know, the initial fact that you need to know that all other facts are based on. Okay. So when we make a plan, we're going to prove that W and Y have the same measure, or X and Z have the same measure. What do you want to know about W and X and Y, angle Y and angle X? Wait, W and X. Oh, what do we know? Sorry. What do we know about W and X and Y and X? What do we know about those two angles for a fact? And what do we know about these two angles for a fact? Well, we know that W and X are a linear pair, and linear pairs are supplementary. So I'm just going to do a little scratch work over here on the side, just things I know to be true. I know that the measure of angle W plus the measure of angle X has to be 180 degrees. Okay, and that's our definition of a linear pair. They're on a line, they add to 180. We also know that the measure of angle Y plus the measure of angle X is 180 degrees. It's just another thing we know to be true. Why? Well, they're a linear pair. Okay, so what else do we know now? Well, we know that they're both equal to 180, so that means they both have to be equal to each other. We can replace this 180 with Y plus X, essentially. Right? So right now, again, I'm just kind of writing what things I know to be true. Doesn't have to be in the right order. We're just writing stuff down. Okay, well, now we have an equation. And what can we do with this equation? Well, we can take X away from both sides, and that says that the measure of angle W is equal to the measure of angle Y, and that's what we wanted to prove. Okay, so now we kind of have a plan. So now we're going to write it out formally. Okay, so this is how we write a geometric proof, or at least one of the ways. We're going to say, all right, our statement number one, the most basic fact, or the thing that all the others are going to be based on, is the fact that these are a linear pair, right? And they add up to 180. So we're going to say the measure of angle W plus the measure of angle X is 180 degrees. How do we know that? That's our reason. Well, we know based on the definition that linear pairs form supplementary angles. Now, it's the reasons that are often the hard part. You're like, well, what am I supposed to say here? The definition of a linear pair, or linear pairs form supplementary angles? And it kind of comes with a little bit of practice and seeing examples, like how you write your reason. But we're going to say linear pairs form supplementary angles. That's something we already know to be true. Statement number two. The measure of angle Y plus the measure of angle X equals 180 degrees. Well, that's the same reason as this one. Okay, so linear pairs form supplementary angles. Okay, based on these two statements, what's the next logical step? Well, if they're both equal to 180, then they're both equal to each other. So that's logically what would come next in this sequence. Okay, so the measure of angle W plus the measure of angle X equals the measure of angle y plus the measure of angle x. Okay, so what reason do we have for doing that? Well, this is a new reason, okay, something that I actually haven't formally given you the name of yet. But all we did was substitute 180 with something that 180 is equal to. So that's just called the substitution property of equality. Substitution. And we'll say property of equality like that. Okay, number 4. Well, remember what we did was we just subtracted x from both sides. And when we did that, we got the measure of angle w equals the measure of angle y. Well, how did we get there? What was our reason for saying that? Well, this is one of these algebra properties. When you subtract x from both sides, we're using the subtraction property of equality. Now, you should have learned these in Algebra 1, but they're not something we say a lot. So if you forgot them, I understand. And then the last statement. Well, we're done. We proved that the vertical angles are congruent. So we say either QED, which is kind of an old way of saying which was to be proved, or we just put like a filled in square that's kind of like a period that says that's the end of the proof. Okay, QED, which was to be proved. I forget what it's Latin. I forget what the words actually are, but that's the main idea. It's Latin for which was to be proved. Okay, we'll do some more of these in class. We'll practice it. We'll just formally write out reasons and justifications for everything. All right, thanks. And this is a little longer than I thought. I'm sorry about that, but I won't put questions at the end.